Welcome back, AP Statistics, for this fourth and final segment of Chapter 16. We're going to be talking about something called the normal approximation of the binomial model, okay? So here's an interesting situation in which the binomial probability model has historically needed some help. Now, with things like binom CDF, it's less necessary, but you still need to know it for AP Stat, okay? The probability of passing a particular challenging test is 60%. If students, 100 of them, take the test, find the probability that more than 70 students will pass. Now, assuming you don't have binom CDF, we're going back in the day here. What makes this problem so difficult? Well, let me tell you. If I have more than 70 students passing, well, one instance in which that could happen is if 71 students pass, right? So I need to find the odds that 71 students pass. I could also find the odds that 72 students pass, and 73 students pass, and 74 students pass. That's a lot of computations. So we're talking like 30 computations here. That's a lot of work. So here's the big breakthrough for how to deal with a situation like this historically. We're going to consider a simulation of 100 trials. That is, 100 times the group of students take the test, assuming that the pass rate is 60%. What do we notice about the distribution of the number of students who pass, and do they seem to follow a pattern? Now, I'm referring to this plot down here, this dot plot, which is the number of students out of 100 who pass per administration of the test. And I used a neat little applet from a website called Rossman Chance. If you want to check that out, it is well worth your time if you want to do a little statistics nerding out using all their applets. But I used one of their applets to create this. What this means is for every dot, I simulated 100 students testing. And the applet then computed how many students passed in that trial and put a little dot down. Now you'll notice that these dots seem to follow a pattern. The pattern that they follow it's not perfect, but it's bell-shaped. And if I were to do more than 100 of these trials of 100 students each, then the bell shape would be all but perfect. So we can say a random variable that fits a binomial model is approximately normal if the sample is sufficiently large and you're about as likely to succeed as you are to fail. But if your sample is really big, then it really doesn't matter how likely you are to succeed and how likely you are to fail. So we need to expect at least 10 successes and at least 10 fails. This is actually kind of up for debate among statistics textbooks, but according to College Board, you need 10 successes and 10 fails. I've taught out of a book that says you only need 5 successes and 5 fails at minimum. We have higher standards here, I guess. So the success-fail condition, n times p is greater than or equal to 10. N times q is greater than or equal to 10. If that is so, then the sample size is sufficiently large, or even if the sample size is not exceedingly large, you are about as likely to succeed as you are to fail. So there you have it. Now we're going to solve the problem on the prior slide using a normal probability model, which, if you remember, is normal CDF. That's one computation. We first need to find the mean and standard deviation, and we need to express the model in the form normal, mean, standard deviation. But there is a step we need to do first. It is subtle, and it's called correct for continuity. So the binomial probability model is discrete. You can only get a whole number of successes and fails, but you already knew the normal probability model is continuous. It's a continuous curve. That means we're going to have to do some doctoring to our statement of what probability we're trying to find for our random variable. To use the normal approximation for the binomial model, we need to correct for continuity. That means that the binomial probability model is discrete, not continuous. So we need to take account of that when we are using a continuous probability model like the normal model. This chart will help you convert between a statement of probability for a random variable x in a binomial sense over on the left, and how to approximate it using the normal model on the right. And if you have questions about this, why this works, this is a little bit messy to explain. Feel free to ask in class and I'll explain it to you, but for now, I'll just let you think about why this is true. So back to our original problem, we're finding the probability that more than 70 students will pass. So we're going to let X be the number of students who pass. Since N times P equals 60, which is greater than or equal to 10, and N times Q equals 40, which is greater than or equal to 10, X is approximately distributed normal with a mean of 60, that's N times P, and standard deviation square root of N times P is 60 times the probability of failure, 40%, which is 24. So it's the square root of 24, pardon the little square root sign there. Would like to have a little bar on top, but can't always get what you want. So X is approximately distributed according to this, and this uses the normal approximation of the binomial probability model. Okay, so now what we're going to do is a familiar process, almost. We have probability X is greater than 70. This arrow we're just going to use here to indicate we are correcting for continuity. Using the correct for continuity rules, X greater than number would be X greater than number plus 0.5. So probability X is greater than 70.5. We throw that into normal CDF. We have our lower bound, our upper bound, arbitrarily high number, and 60 is our mean. Standard deviation is the square root of 24, again with this silly little abbreviated radical over here, which would get us 0.016. And if you're curious, binom CDF yields an answer that is a 1/10 of 1% away. So this is a very accurate method that statisticians could use for a long time. Let's do some more practice with the normal approximation to the binomial model. The communications monitoring company Postini has reported that 91% of email messages are spam. That stat doesn't get any better the more I see it. Recently, you installed a spam filter. Good on you. About time. You observed that over the past week, it okayed only 151 of 1,422 emails you received, classifying the rest as junk. Should you worry that the filtering is too aggressive? So, what is the probability that no more than 151 of 1,422 emails are real messages? Okay, so here we go. We want to make sure that we can use the binomial model in the first place, and then we want to make sure that the binomial model can be approximated by the normal model. These messages do represent less than 10% of all email traffic, so the 10% rule is abided. There's a clear success fail. Either an email is spam or it is not, success being not spam and failure being spam. And the probability does not change, okay? There are, these trials are, the email traffic is way more than what we're accounting for, those 1,422 messages. So less than 10% of the population, we can assume independence of events. So we can model this with a binomial model, but we can do even better. N times P is 127.98. Last I checked, that is bigger than 10. And N times Q is way bigger than 10. So it is okay to approximate this binomial probability model using the normal model. And here is how we shall do it. Okay, we're going to find the mean and standard deviation first, and then we're going to correct for continuity, and then we're going to find that probability that there are no more than 151 of 1,422 emails. Okay, so we're going to find the mean and standard deviation. We're going to let X be the number of real messages. Since N times P is greater than or equal to 10 and N times Q is greater than or equal to 10, we can use this approximation. Normal model, mean is 127.98. Standard deviation is 127.98. That's n times p times q is 0.91, and square root that. We would say the probability that x is less than or equal to 151 would correct for continuity to x is less than 151.5. If we have probability that x is less than or equal to a number, that's the same as probability x is less than 151.5 if we're using a normal approximation, okay? So our correct for continuity would yield this. If we were to put that into normal CDF, we would have the mean of 127.98. Standard deviation is this square rooted expression. We would have a maximum of 151.5 and a lower bound of just arbitrarily low number, negative 1099. And that would yield about a 98.5%. So there's a 98.5% chance of getting no more than 151 out of 1,422 emails. So that's a pretty high probability. That actually means that we could do to be more aggressive, all right? 151 is actually a high number of normal emails. We're expecting something closer to the 120s, all right? It is very likely that we are within 151 emails, so we can actually do to be more aggressive with our spam detection. And now you get to aggressively tackle this homework assignment. Have a great day.